In this presentation, we're going to go through something called instant design. I need to give credit to one of my professors at the University of Texas at Austin, Dr. Richard Klinger, who taught me about this concept. The idea of being able to instantly design on the back of an envelope beams, columns, shear walls, and slabs. By the end of this presentation, I want you to be able to apply instant design principles to design typical reinforced concrete beams, columns, shear walls, and slabs, all in under 20 minutes. We'll start by looking at the instant design of beams. So the first step is to determine our loading. Our loads can be found using ASCE 7. We'll have our dead load from our slab, which we'll assume is 8 inches for deflection and shear, and that gives us about 100 pounds per square foot. We have our HVAC load of about 20 pounds per square foot, giving us a total dead load of about 120 pounds per square foot. Our live load here is going to be 50 pounds per square foot, a typical office load, plus 15 pounds per square foot for partitions. We can reduce our area by about 0.8 based on our tributary area. So with a larger tributary area, it's less likely that's going to be loaded to the maximum load simultaneously. So reducing our live load by 0.8 gives us a live load here of 52 pounds per square foot. We're going to assume for this initial design that we have 20-foot bays, so 20-foot column spacing with 24-foot columns. We can factor our loads using our typical ACI 318 load combination of 1.2 times the dead load plus 1.6 times the live load to give us our factored surface load of 227 pounds per square foot. And then we can use our tributary area to find our distributed load that will apply to the beam. So we have a 20-foot column spacing, so 20 feet is our tributary area for our beams. So 20 feet times our pressure load gives us a distributed load W sub U of 4.5 kips per foot. We're going to assume that we have continuous beams from one span to the next. So we're going to use ACI 318 analysis simplifications. On the exterior face, we have WL squared over 16, negative moment. Interior face, a negative moment of WL squared over 10, and a maximum positive moment in the center, WL squared over 14. We can use these approximate moments to find our maximum required negative moment. So here you can see our maximum required negative moment is 1750 kip inches. We can divide this by 0.9, our phi factor for flexure for a tension controlled behavior. So we're assuming tension controlled behavior here. And we'll get an MN required of 1,944 kip inches. We can use this expression here for our flexural capacity to find our B and H. So we'll start with our B value here. We'll assume a rho or reinforcement ratio of 0.01, a concrete strength of 4 KSI, and a yield strength of 60 KSI. Using these values, we can calculate our omega as about equal to 0.15. We can set our MN required that we found on the previous slide equal to the moment capacity expression that was shown on the previous slide in terms of omega, and plug in our known values for omega, F prime C, and omega here, and see that we need B d squared equal to about 3,554 inches to the third. We can say that the ratio of D over B is about 1.5. So we can calculate our B equal to 11.6. We want to round this to the nearest whole inch, or we can round it up here to a B equal to 12 inches. So typically we'll round it to a whole inch, and typically we'll round it to an even inch as well, just to make it more constructible. Our height in this case, we're going to use our rule D over B about equal to 1.5, and so here we'll have a H about equal to 20 inches. So we're going to start with a section here of with a B of 12 inches, and an H of 20 inches. We can also remember our rule of thumb when determining our H. So a typical rule of thumb is that the height of the section in inches is equal to the length of the beam in feet. So here we had a 20-foot span, so our 20-inch deep section matches up with that rule as well. A practical layout for our reinforcement is shown on this slide, where we'll have 2 bars coming out in negative reinforcement of our exterior column, overlapping with an additional 2 bars starting here in span 1 and extending through span 2, and then another 2 bars starting here in span 2 and extending to span 3. And then you have 2 bars in the positive moment region. So essentially in the maximum negative moment region, you will then have 4 bars. In the negative moment region on the exterior span where the moment demand is less, you'll have 2 bars, and then the positive moment region where moment demand is less, you'll also have 2 bars. So we're going to try to design the beams on the following slides with this reinforcement layout in mind. We want to try to use a single bar diameter for all of our longitudinal steel. Using the same bar diameter makes the structure more constructible. So on the job site, a number 8 bar looks very similar to a number 9 bar and a number 7, so they can get confused. But if you have all number 8s, then you know that all of the bars will be number 8s in the final structure. So we're going to assume to start number 8 bars, and we're going to assume at our maximum negative moment region we have 4 number 8 bars in the top and 2 number 8 bars in the bottom. We're going to assume that we have 1.5 inch cover to the ties, and we'll assume number 4 ties spaced at 8 inches on center throughout. And we'll place the first tie 4 inches from the column face to satisfy code requirements. So then our D is just our overall height, 20 inches, minus our cover, 1.5 inches, minus the diameter of our tie, a number 4, so 0.5 inches, and minus half the diameter of our longitudinal bar, which is 0.5 times 1 inch. So we'll have a D here equal to 17.5 inches. We can check to see our required steel area by using our approximate equation for AS required. Here we're assuming that our lever arm is going to be equal to 0.9 times D, and we'll use our MN required from a couple slides ago. So we can find our AS required equal to our MN required 1,944 kip inches divided by FY 60 KSI times 0.9 times D 17.5 will give us our AS required of 2.1 square inches. So last slide we said we were going to try using number 8 bars. So we can try using 4 number 8 bars, which gives us a total area of 3.16 square inches. Now that we have our actual section dimensions and our steel area, we can analyze our section and calculate our actual nominal moment capacity and compare it to our MN required that we found at the start of this example. So our C from equilibrium will have equal to our tension force, ASFY, so 3.16 square inches times 60 KSI, divided by 0.85 times F prime C 4 KSI times our beta 1, which depends on our F prime C. So for 4 KSI, our beta 1 is 0.85. And then our B, our width of the beam is, our width of our compression block is 12 inches. So that'll give us a C of 5.47 inches. We can then sum moments about the centroid of our compression block, and we'll get our moment equal to our tension force, so ASFY 3.16 times 60 KSI, times our lever arm, the distance from the center of our tension force here in our steel and the centroid of the compression block. And we have 17.5, so D minus beta 1 0.85 times C 5.47 divided by 2, which gives us a nominal moment of 2,877 kip inches. This is greater than our MN required, so which is 1,944 kip inches. So now we're ready to move on to our positive moment design. Our positive moment demand is equal to WL squared over 14, which will be 1,250 kip inches when we plug in our factored load and given span lengths. And that'll gives us an MN required of our MU divided by 0.9. So we're assuming a phi equal to 0.9 for tension controlled, which gives us an MN required of 1,389 kip inches. We have our section geometry already. We're going to use the same section shape for the entire length of the beam. So 12-inch width, 20-inch height. So we can get our AS required equal to our MN required divided by Fy times 0.9D. So 1,389 kip inches divided by 60 KSI times 0.9 times 17.5 gives us an AS required of 1.47 square inches. We can try 2 number 8 bars, which gives us a value here of 1.58 square inches. So now we have our area and we have our section geometry, so we can now check our actual capacity. We can find the actual capacity of our positive moment region similar to the negative moment capacity. So we find our C from equilibrium, and all we're changing is our area of steel here. So we have a C here of 2.73 inches. And then we can find our nominal moment, again changing our area of steel and updating our C in the equation to get a nominal moment here of 1,550 kip inches. We can see that this nominal moment is greater than our MN required, so our positive moment is okay. Some other common detailing checks. We need to make sure that we develop the negative moment reinforcement, which we do if we extend it 1/4, or if we extend the reinforcement 1/4 past the column. We need to, or a common detailing check is to extend the reinforcement 12 dB past what's required. So we're doing that. Extend 1/3 of our negative reinforcement past required moment regions. So we're extending a half of the reinforcement pass, so that's okay. And extend 1/4 of our positive reinforcement into the supports, which we're doing here. Next, we need to check shear. So our shear demand, our V sub U, is just V sub U times L over 2, which we find to be 40.5. So our Vn required is then that value divided by our phi factor for shear, 0.75, which gives us a Vn required of 54 inches. Our shear resistance provided by our concrete we can find with our ACI 318 expression. So we have no applied axial load, so we lose the second term. So we'll get VC equal to 26.6 kips. Our VS, again, we can use our ACI 318 expression, and we can find that we have a shear contribution of our transverse reinforcement equal to 52.5 kips. Adding those together gives us a total shear resistance of 79.1, which is greater than our VN required of 54 kips, so our shear design's okay. We can next check our deflections. We need to remember that the ACI 318 minimum thickness check is an alternative to calculating the deflections. So our thickness or our height of the section, 20 inches, is greater than or equal to the minimum thickness requirement for this type of structure, a continuous structure, L over 21, which is 10.3 inches here. So we're okay. So the beam is thick enough, so we don't need to check the actual deflections of the structure. We need to make sure that the bars are able to fit within the width of the beam. So we're going to check our spacing here. Our beam width, needs to be greater than or equal to 2 times our cover. So we have cover on each side, plus 2 times the diameter of our stirrups. So we have stirrups on each side, plus 2 times the radius of the bend, which is the distance from our bar here to the centroid of this bar here, which will be 2 times the diameter of our stirrup, plus n minus 1 dB. So that's the total number of bars that we have, 1, 2, 3, 4, minus 1 diameter of the bar because we're taking into account that through our bend radius. And then finally, the number of spaces that we have times the spacing between the bars, where our space here is the maximum of 1 inch and our bar diameter. For our number 8 bars, we'll get that our B needs to be, or our B equal to 12 inches is greater than or equal to the required B of 12 inches. So you can see that our B here of 12 inches is going to work for up to 4 number 8 bars. If we have more than 4 number 8 bars or a larger bar diameter, then we need to have a wider section. We also need to check our maximum spacing requirements. So from ACI 318, our spacing needs to be less than or equal to the values shown here for crack control. So our spacing needs to be less than or equal to 10 inches, which we get from this equation here, and also less than 12 inches. So as long as we're less than 10 inches, we're okay. The spacing between the bars is the total base width minus 2 times the cover, so we have cover on each side, minus 2 times the diameter of our stirrups, we have stirrups on each side, minus 2 times our bend radius, and which will be 6 inches here. So our 6 inches is less than 10 inches, so our our bars in this beam will check the maximum spacing requirements. We also need to check our tension control limit. So our tension control limit is for grade 60 reinforcement is going to be 0.005. So that's the strain in our tension steel at time of failure. So we need to have a strain in the tension steel greater than 0.005. What we can do is we can solve for our C based on the strain diagram and get a C equal to 3/8 times D. And then we can use that C with our equilibrium expression to solve for rho tension controlled. So our rho tension controlled here is 0.018 with our 4 KSI concrete, our 60 KSI steel, and our D of 17.63 and our B of 12 inches here. So our rho of the beam is equal to 0.015, which is less than or equal to our rho tension controlled of 0.018. As long as we're less than our tension controlled rho, we'll have tension controlled behavior. Our final design for our beams is shown on this slide. You can see we have 3 different sections. Our section AA here at the end, where we have 2 number 8s in the top and the bottom. Our section BB here, where we have 2 number 8s at the top and the bottom still. For our positive moment, AA is our negative moment on the exterior span, and C is the negative moment region on interior spans. So all the interior spans are going to have a section CC, where we have 4 number 8 bars at the top and 2 number 8 bars in the bottom. So this will satisfy our design requirements for a 20-foot span length. We can easily modify the design to other span lengths. So we designed a 20-foot span length on the previous slides, but if we were to change the column spacing to 22 feet, we would need a section depth of 22 inches, a base width of 14 inches, and number 9 bars in the same configuration that we had our number 8 bars. For a 24-foot span, we need a 24-inch deep section, 14-inch width, and number 10 bars. 26-foot span, a 26-inch depth, 14 inches width, and number 10 bars. And a 28-foot span, a 28-inch depth, and 16-inch width, and number 11 bars. So you can see with these basic column spacings and span lengths, we can quickly get a design that'll satisfy all of our ACI 318 design requirements. Next, we're going to look at instant design of columns. And the first step of this will be to determine our loading, again, based on ASC 7 and the self-weight of our slabs. So similar to the beams, we'll have a dead load of 120 pounds per square foot and a live load of our 50 pounds per square foot office load plus 15 pounds per square foot partitions. And this time we're going to reduce by 0.4 based on our tributary area for our columns. So our live load will be reduced by 0.4, so we'll get a live load now of 26 pounds per square foot. We can factor this load the same way that we did for our beams, 1.6 times our dead load, and 1.2 times our dead load and 1.6 times our live load to give us a total load. And we're just going to round up for simplicity and to include the self-weight of the columns. So we'll have 0.2 kips per square foot as our load that we'll move forward with. We'll design the first floor column based on the total number of stories n. So we have a 20-foot column spacing, so our total load is 0.2 kips per square foot times the tributary area for each column is 20 feet squared times the number of stories gives us a total load here of 80 times n. We're going to assume here that we're working below balance, and we'll assume that we have a 2% reinforcement ratio and a 6 KSI concrete strength. We can remember from before that we want to be below balance, and that balance is typically about 1/3 of our pure axial capacity. So with this in mind, we can say that our P naught is equal to 3 times P sub U divided by our phi factor. We will assume here that we have a phi factor somewhere between compression controlled and tension controlled. So we'll just assume initially that we have a phi of 0.75. And we know from before that our P naught, our pure axial compression strength of the column is equal to 0.85 times F prime C times AG plus rho times AG times Fy. So here I'm not taking out the steel area from our concrete area, but again, this is an approximate equation, so we'll just assume this is okay for now. So then we'll have a P naught plugging in our concrete strength and our yield strength for our steel. We'll get a P naught equal to 6.3 times our gross area. And we can solve then for our gross area by setting our P naught equal to the 3P sub U over phi. And we'll get a gross area of 50.8 times n, which is about equal to 50 times n, where n is the number of stories. The size of our column then can be based on that expression. So if we have 5 stories, we'll have a required gross area of 250 square inches. So our column dimension can be 16 by 16. For 10 stories, we'll need 500 square inches, so we'll start with a 22 by 22 inch column. And for 15 stories, we'll need a gross area of 750 square inches, so we can use a column that's 28 inches by 28 inches. So we can select the number of stories and with our area, we can choose our steel based on a rho about equal to 0.02. So for a 10-story building, we would need a 22 by 22 inch column, and we would need steel about equal to 0.02 times 22 inches squared, or about 9.7 square inches. If we use 8 number 11 bars, we'll get a little bit more than what our required steel is, so we'll start there. Note that if you were to do a more detailed calculation and use the moment axial interaction diagram, you could find that you'd need about 8 number 9 bars would be sufficient. But this is a quick way to get an approximate column size and number of bars. So for an approximate method, you give up some, you have more conservatism built in. Typically, if we use number 4 bars spaced at 4 inches on center, this is going to work, and this will satisfy your shear, your confinement, and your spacing requirements. Next, we're going to look at our instant wall design. And for this, we're going to look at our below example with and assume a reinforcement layout. We'll assume loading of 10 kips on each story, a 10 kip lateral load, and we'll assume our loads per floor are about the dead load about 100 pounds per square foot, the live load about 400 pounds per square foot reduced, and we're going to use a load combination of 0.9 times our dead load plus 1.0 times our wind load. We'll assume we have a 4 KSI concrete strength, grade 60 steel, and 1.5 inch cover to our reinforcement. And our walls, we'll assume that we have a 20-foot wall. So the typical reinforcement layout, a good starting point for a basic wall is having number 4 bars at 12 inches in each direction. So that's the layout that we'll start with. Note that our wall has a height to base ratio of 30 feet over 20 feet, equal to 1.5. This is the borderline between high rise and low rise, but we'll take care of that in our shear design. We need to check to see if our flexural reinforcement is sufficient for the design. So the first thing we would need to do is develop a moment axial interaction diagram for the wall. So shown here is the moment axial interaction diagram for the wall that we're looking at, our initial design. We next need to calculate the demand that'll be placed on the wall. And we'll do that using our approximate tributary areas of 20 feet by 20 feet or 400 square feet. So with our dead load and our live load and the load combinations that we said we were going to use, we'll get an axial load here of 108 kips and a moment here of 7,200 kip inches. We can plot that on our moment axial interaction diagram and see that we are within our diagram. So our design is sufficient for our flexure. Next, we need to check our horizontal shear reinforcement. You can see here I found the axial load and moment and shear demand using a different load combination than we did before. But anyway, the only value that we'll need for ACI 318, the current ACI 318 is our shear, but ACI 318.14 and earlier, you also needed the axial load and moment when you were calculating the shear capacity. So that's why I'm showing them here. So anyway, our shear demand on our walls is going to be 15 kips. We can calculate our shear capacity of the section using our VN expression from ACI 318. You can see here our HW to LW or height to width ratio is 1.5. So for an HW to LW ratio less than or equal to 1.5, we'll have a alpha C factor of 3. The area of our wall is just the length of the wall times the thickness, so 240 inches times 12 or 2,880 square inches. And then our reinforcement ratio is just 2 times 0.2 times 12 inches over 12 inches, which will be 0.00278. We can plug all of these values into our VN expression to get the value here. And we'll see our shear capacity is 1,027 kips. We need to compare this to the upper limit provided by ACI. So the upper limit is 8 times lambda times the square root of f prime c times a sub cv. So plugging in the values for our wall, we'll get an upper limit of 1,457. We can see that our VN is less than this upper limit, so we'll use 1,027 kips as our VN. We need to take our phi for shear of 0.75 times our VN 1,207 kips to get our phi VN of 770 kips. We can then compare that value to our V sub U, and we can see that our phi VN is greater than VU, so our design is okay. We also need to check that we have sufficient horizontal shear and vertical shear reinforcement based on our ACI 318 limits. So for this wall, our rho t needs to be greater than or equal to 0.0025, which is the case, so we're okay here. And our longitudinal reinforcement ratio also needs to be greater than or equal to 0.0025 and this equation here. And in both cases, these are true. So we have sufficient horizontal and vertical shear reinforcement. Next, a few other notes. We need to make sure that all of our reinforcement is properly anchored. So to do this, we need to ensure proper development of the reinforcement in the base of the wall. And we need to make sure that we're hooking the reinforcement at the top of the wall. And this makes sure that we have development of the reinforcement at the bottom and the top. We also need to check our shear friction capacity at the base of the wall. So typically sliding shear can be delayed if our shear stresses are less than about 6 times the square root of F prime C. So we can check our sliding shear capacity. And also, if we need more flexural capacity, which we normally won't, we can add vertical boundary elements. So we can group our reinforcement at the ends of the member and enclose them in confining steel. And to see more details on this, you can go back to the module on shear walls. On the next couple slides, we're going to look at instant slab design for two-way slab sections. And note that a two-way slab system would be used separately from beams, so this is a kind of separate design. But again, we would be looking at or in this example, we're going to start with a 20-foot by 20-foot column spacing. We can again look at our loads, and we can have a 120 pound per square foot dead load and 50 pound per square foot live load with a reduction factor taking it down to about 40 pounds per square foot. We can factor this load using our normal load factors, so 1.2 times dead and 1.6 times live, which will give us a design ultimate load here of 200 pounds per square foot. And we're going to assume that about half of that goes in the X strips and half of it goes into the Y strips. So that means that we'll design our design moment that we'll design for in each direction is Q sub U times A squared over 8, and then divide by 2 to get an equal moment going in each direction. So that gives us about 60 kip inches going in each direction. So we'll also make the assumption that our midspan moment is equal to our support moment. So our m naught divided by 2 will be our max moment at the midspan, and m naught over 2 is going to be the max moment at the ends. And that's what we'll be assuming here. Because of that assumption about half of our max positive moment 0.5 m naught and max negative moment 0.5 m naught, our AS required is going to be 1/2 of our m naught. We can divide that by phi times Fy times an approximate lever arm 0.9 d to get an approximate value for our required area of steel, AS required. So here we can have an AS required of 0.095 square inches per foot. Our other requirements is our maximum spacing is going to be 18 inches, and our minimum reinforcement ratio is going to be 0.0018. So our AS min will control here with 0.18 square inches required per foot. And we'll use these values to design the slab steel in both directions. Using the reinforcement ratios from the previous slide, we can see that if we have number 4 bars spaced at 12 inches in each direction, we'll satisfy our design requirements and also our minimum steel requirements. We can extend our top bars 5 feet into the slab from the adjacent spans, and we can extend our bottom bars all the way to the edge of the beam regions. So doing this will satisfy all of our slab design requirements. Next, we need to calculate the demand on our beam regions. And we can do that using the expressions shown on this slide. So essentially, we'll take the strip of a slab and we'll see what the demand is going to be on our beams. So we'll take a Q over 2 times A over 2 going into our beam region on the right side. So we have then a demand here of Q times A divided by 4. So you can see the maximum moment here, assuming the ends are simply supported, would be our load. So our distributed load times A squared over 8 will be Q times A to the third over 32. We will again assume that the maximum positive moment is m naught over 2 and the maximum negative moment is m naught over 2. So we add in a times 1/2 here to get our maximum negative moments and maximum positive moments in our beam. We can then find our m naught, or our maximum moment in the beam, and the maximum moment at the support, equal to just 1/2 of that m naught that we found before, which in our case will be 300 kip inches. We can find our AS required then by taking our m naught divided by phi, so we're assuming tension controlled 0.9 times Fy is 60 KSI, times our approximate lever arm 0.9 times D. So 0.9 times 6.5. So we'll get an AS required here of 0.95 square inches. So in our beam regions, we're going to need 5 more number 4 bars on top and 5 more number 4 bars on the bottom in each of our beam regions. We could use larger bar sizes if we wanted and use less of them, but just because we're using number 4s in the rest of the slab, we'll go ahead and use number 4s in the beam region as well. So in our beam regions, we'll need 5 more number 4 bars on top and 5 more number 4 bars on bottom. And we'll extend the negative bars 5 feet into the adjacent slabs. So doing this is going to take care of our beam design for flexure. And this will conclude our instant slab design for our two-way slabs. And that concludes this lecture on the instant design of beams, columns, shear walls, and two-way slabs.